Hi guys, welcome grade 10s to Life Sciences. I am Looney. Cheryl,
Afternoon, everyone.
how are you?
I'm fine. Are we better this week? Are
Yes,
not so
you see,
tired?
I'm not choking.
I'm about to say.
Yeah, I'm fine. I'm not dying. I'm much better. What are we doing for the grade 10s
We're
today?
looking at Diecut stems, especially secondary growth.
All
today.
right. Mindset, as you heard it, we're doing the Diecut Stems, and I hope you guys will enjoy the show. How to get a hold of us on Facebook, it's facebook.com/learnextra. And then on Twitter, we are at learnextra. And then remember, you can download all the show notes, the videos, and the schedules on learn.mindset.co.za. And then, guys, if you want to win yourself this awesome calculator, all you need to do is complete the test yourself questions and the entry form. It is on our Facebook page. I posted everything on Facebook, so you don't have any excuse, and you have until Friday at 12 to enter. So you can watch the show, then you can maybe go relax, then maybe at 9 you can say, maybe I want to enter the competition, but you have until Friday at 12 to enter. Congratulations to Qini Sombalana for winning yourself this awesome calculator, proudly brought to you by Casio.
My turn now.
Yes.
Are you going to finish eating your sweet that you started
Yes,
eating
of course.
just
Why
now?
do you need to expose me to the people?
Just in case they hear just now. Oh, welcome grade 10s to yet another Learn Extra Live. We are still busy with our plant section, and if you tuned in last week, you would have seen that we paid particular attention to dicotyledonous plants, right, especially the stems and the roots. And this week we're going to have a look specifically at our dicotyledonous stem. And as I started to talk a bit about it last week, we're going to be looking at a process called secondary growth. All right. So in dicotyledonous stems, the structure is able to lead to this process called secondary growth. First of all, one I always forget, our challenge question. Right, you know me, I'm always a multiple choice question. And the question is quite straightforward. It says, annual rings are distinct in plants growing in, right, and I give you 4 different kinds of regions. Temperate, which is another word for mild, moderate, tropical regions, polar regions, and Arctic regions. All right, so which one do you think you're going to find annual rings are going to be more distinct in? Just carry on listening to the program, and if you listen, you're going to find out the answer pretty quickly. Okay. If we have a look at our plants, all right, let me just quickly extend here. Oh, there we go. Right, if we have a look at our plants, we're going to find that plants are obviously going to grow, all right? So, where do plants grow? If we have a look at the diagram, right, we're going to see, and remember we did right in the beginning, right, when we did plant tissues, we looked at this tissue called meristematic tissue. All right? Meristematic tissue was specialized tissue that could divide by mitosis, all right, for growth, all right, repair, replacement. You remember we did mitosis? But what it does though, meristematic regions obviously allow the plant to grow. Meristematic tissue is embryonic tissue, all right? It doesn't become differentiated. So in our plant, a plant will grow. The roots will grow downwards, all right? That is called an apical meristem. Apical means at the points, all right? And at the top, let me use a different color because it clashes so nicely with the green. At the top of the stem, all right, plants are going to grow upwards because that is the apical meristem. Roots grow downwards, right? That is still an apical meristem because it's still at the end of the roots. If you remember, when we looked at roots last week, all right, we saw the root, we saw a very distinct region, the meristematic region, which caused the root to grow downwards. Okay, so this is what we call primary growth. When the plant, the stem growing upwards, the root growing downwards, that is primary growth. Now, last week again, we looked at this thing called a dicot, all right, a dicotyledon. And we said that a dicotyledon, if we open up, all right, if we were to open up the seed, we would find 2 little parts, di meaning 2 parts within the opening of the seed, whereas monocot, we only had the 1, mono meaning 1. Now that, whether it has 2 or 1, will influence, all right, how the stem or what the plant looks like, its characteristics. Okay? Now, in certain plants, especially woody plants, okay, that are dicotyledonous, they are not only going to grow upwards, all right, usually plants that live for longer than 2 years, all right, and we call them perennials, all right. The word over here, let me write it, hope I don't spell it wrong. All right, they are called perennials. Oh, there we go. That means they're going to have a much longer lifespan as opposed to your annuals, all right, like millies, which grow a season, we harvest them, and we regrow them again. Okay, so now because the plant is going to live longer and it's going to grow bigger, all right, what we need to do is support it more. Okay, support it more. So what's going to happen is the stem of some dicots, not all, especially our woody, all right, the wood, the trees, okay, not how herbaceous. Herbaceous is our green ones that are flexible. Our woody trees, all right, so because they're going to grow so big, all right, we need to be able to grow wider to be able to support that. Now, if primary growth is growing upwards and downwards, okay, excuse me, okay, growing wider, all right, is going to be called secondary growth. We can call it secondary growth, we can call it secondary thickening, all right, and we're going to have tissue. We're going to have tissue within the stem, all right, that is going to divide so that we are then able to increase the width of the stem. Okay, let's go over the internal structure of a dicot stem that we did last week. This should look familiar to you, all right? I just did a simple drawing over here. If we look at a dicotyledonous stem, all right, we said last week it's got a very particular inner structure, okay? So if we were to look what the inside looked at, we had this very distinctive circle, all right, of what we called vascular bundles, okay? They were in a distinctive pattern. They were in a circular form. We don't do monocot stems, all right, because we are concentrating on dicot, but if I were to draw, all right, a monocot stem, the vascular bundles are haphazardly. They placed all around the stem. There's no pattern. All right. Now the dicot stem, that pattern is very important for its ability now to grow outwards. Okay? So the dicot stem, those vascular bundles, all right, are in a circular form, as you can see. Now, if we were to have a look at the vascular bundle, okay, it's got a little hat of sclerenchyma, right? And then the three regions we're going to concentrate on are these three that I've joined. One, the phloem, all right? Two, the xylem. And then the star of the show today, all right, cambium. Cambium is meristematic. All right, it's secondary meristematic. What we're saying, it's meristematic tissue. Cambium has the ability to divide by mitosis and give rise to new cells. Now, it's in between the xylem and it's in between the phloem. All right, so we can then assume that it's going to give rise to new phloem and new xylem. Okay, right. Not only that, if we have a look at the stem, what happens is, let me go down a bit, all right? Within this, I've drawn this pink circle there and now from here to here, okay? What happens after the first year? These cells over here are all parenchyma, okay? They're all parenchyma cells. between the vascular bundles. And what happens to those parenchyma cells is they become meristematic as well. All right? So that when they become meristematic, you've got this ring. Keyword for today, you've got this ring, all right, of meristematic tissue that is going to be able to, sorry, I've got an itchy nose today. I think somebody's going to fight with me. So my nose is itchy and I'm going to, you're laughing at me. Maybe I need one of those holes. All right, so the meristematic tissue, all right, is going to divide to make more xylem, and it's going to make more flow, okay? How does it do that, all right? How does it do it? Now remember, if we're talking about a circle and we put more phloem down going outwards and we put more xylem going inwards, what will happen to my plant? All right, my stem will increase in girth. Girth means width, all right? So it's going to get wider. Remember, we do want it to get wider. Why? The wider it is, the better it's going to support the big trees, right, that are usually going to undergo the secondary thickening. Okay, so let's have a look a little bit closer. Right, the diagram sometimes is a little bit confusing, but let's go through it. I want you to have a look at this diagram over here. Okay, there we go, me and the smart board today. If we have a look at this, this is exactly the same diagram as I've just put up there. All right, what do we have? The most prominent thing, there we have our round vascular bundles. Okay, there we have them. And if you will notice, there are 3 shades, all right? There are 3 shades. We're not going to look so much at the sclerenchyma cap. What are we concentrating on? We're concentrating on phloem, we're concentrating on xylem, and there in between each of them, we are going to find cambium. Okay, all right. Now, what does the meristematic tissue do? It produces new xylem, and it makes new phloem. So let's have a look at this diagram right next to it, okay? Looks very confusing, but let's have a look. Look at the green one. Let me use a different color. I think pink would be better. Have a look at the green over here. The green is the phloem. What you will notice, all right, there is the original, all right, the phloem that was there right from the beginning. Can you see there? I've circled all of them. All right. And what we call it, because it was the first one there, we're going to call it primary phloem. Okay. Now we're going to go into the middle. Now I'm going to use, let me use yellow. All right. This one over here. Can you see here? This was the very first xylem. This was the very first xylem, all right? So it's the very first xylem that was there. So we had primary phloem, the first phloem. Then we have primary xylem, the first xylem. But now, if I look at it, all right, what on earth are these 2 things in the middle? Okay, what is this? If xylem makes new tissue, there we go. This is new xylem. This is all new xylem, all right? All of that, because what is there? What are we going to find? Let me choose another pen there, the green. What's this green here? Isn't that the cambium? There we go. That's the cambium. All right, so what does it do? It makes new xylem. So the old xylem gets pushed further inside. This is new xylem. All right, and where's it going to make new phloem? On the other side. So there's the old, this is the new. So the new is called secondary xylem. It wasn't the original one there, all right? It was there secondly. I know that is totally grammatically incorrect, but it was afterwards. So what happens is, if we have a look, here is the xylem, all right? And here is the phloem, And what do you notice? Because, all right, they are in concentric rings, it's going to form a ring. Okay, look here, because the vascular bundles are round, all right, when they lay down new xylem and new phloem, the tissue forms this ring, right? And that ring is what we call an annual ring. All right, what do we mean by that? This is what we mean by it. All right, this is what we mean by it. Are we going to take a break and then we're going to come back and show them exactly?
Okay.
Or do you want to? Can I
Want to
carry
show
on?
them now?
Do you want to show them?
Yes, we
All
can
right,
show them.
Okay, James says we're going to show
them.
you. All right, guys, I want you to have a look at this block I've got here, and I want to say thank you to Leon, all right, at the school, who got this for me. I really appreciate it. Okay, now when we're talking about annual rings, you're going to see very clearly what we mean. Now, if you have a look at the ring, you are going to notice that there is a dark piece, and in between that, there's a light piece. So you notice the rings are distinctive because there's an outside dark and there's an inside, all right, there's a much lighter color. And that is because, all right, what you're actually seeing is the xylem. The phloem is not so noticeable, it's the xylem. Remember I said to you it makes a ring? Look there, what is that? That is a ring. Because what's in between that space over there? It's going to be the secondary xylem and the secondary phloem. Now, if you have a look, why is there some darker ring and there's a light ring? And the answer to that is seasons. Okay, seasons. The rings of the tree can tell us enormous information about what the climate was like at the time. Because these dark rings over here is when growth starts to, when there's growth during what we call the autumn and the winter months. Okay, so if you will notice, it's not a very, very large area. Water, there's not a lot of water, all right? There's not a lot of growth occurring. Growth kind of comes to a little bit of a halt during the colder months, which means here, this white piece, these white pieces, okay, can you see this is a nice ring over here, all the way around. Those white pieces is when growth occurs during spring and summer. When there's during spring and summer, there's lots of water, the conditions are mild, so there's more growth, all right? So if we've got a spring and a summer, the light, the dark for the winter and the autumn, winter, autumn, spring and summer make 1 year, all right? So from one dark ring to dark ring is 1 year's growth, right? So we can see from here, if we count the rings, we are then able to see how old the tree is. Also, the rings will tell us about the conditions at the time. The further away, all right, the annual rings are from each other, it tells us that the temperature is milder. The closer they come to each other, can tell us, all right, that the temperature was colder. So it wasn't as good a growing season as the others were. So when we look at this, we think it's just rings, but it can actually tell us so much about the history of the tree. Okay, I think that's our block, and then we'll come back.
All right. Mindset says we are going to take a break. Quick shout out to Gabriela Mtokozisi, who says you actually helped him. He got a 75% for life sciences.
Really?
So congratulations to you.
And it wasn't me, it was him, because he pays attention and he works.
All the hard work.
Yeah, all the hard work.
And then Banyana, Apiwe, and Ratabila, thank you so much, guys, for tuning in. But let's take a quick break. Go get yourself some water, and we'll see you straight after this. Welcome back, guys. I hope you guys are still enjoying the show. We are doing Diecut Stems with Cheryl and Looney. Just a reminder, the Learn Extra Help Desk is brought to you by Axel. So if we don't get through your questions, when we take questions right at the end of the show, remember you can send them to learn.mindset.co.za/help desk. That's where you can send all your questions if we don't get through them right at the end of the show. But now it's time for the lesson. So Cheryl.
Karen, my nose is still itching. I tell you what, I think my husband's probably going to fight with me tonight.
No.
Oh, welcome back. All right. We just saw the real life version of the annual rings, our secondary growth, showing how a plant, dicotyledonous stem, is able to grow in width. All right. Now, we've spoken about what is happening on the inside of the stem. All right. So you see all these diagrams over here. What we've noticed, this is our rings. But if we think about it, I spoke about woody trees, the bark. All right, how do we get that? Have a look over here. All right, I'm going to go back one, I think. There we go. In the beginning, if we have a look, all right, at our young stem, we looked at it last week. We find we've got an epidermis on the outside, all right, epidermal tissue. Right, underneath that parenchyma, and then this dark blue, all of that is going to be parenchyma, all right, our cortex. Now, what happens after about a year of growth? In the beginning, all right, in the beginning, when the plant is still growing, these epidermal cells, all right, are still on the surface. The plant does need to be able to bring in, take out water, gaseous exchange. So there is stomata, all right? There are stomata on the epidermis of the young dicotyledonous stem. But after a year, all of that changes, all right? The epidermis here, all right, and the parenchyma, it changes, all right? And if we go back to the next one, we're going to see it no longer says, all right, it no longer says anything about the epidermis. It has now changed. It's become a different kind of cambium. And now you need to understand. If the plant is going to grow wider, all right, that if the epidermis is soft, all right, if we say herbaceous, it's soft and green. If it's going to go wider, it's like me trying to fit into a really small pair of pants, all right? What's going to happen if I fit into the pants? Right, I'm going to sit down and something's going to burst at the seams, all right? There goes my button, or I split my pants or whatever. Exactly the same thing is going to happen to a plant, all right? It's growing wider, so it needs to have a covering that is much harder, that is able to support this increase in width, okay? So we need to change the makeup a bit. So how do we do that? All right. What we do is the epidermis and the epidermal cells and the parenchyma cells, the cortex, they change and also become meristematic. All right. But what they form is this cork cambium. All right. Cork cambium. Much harder. All right. And on the outside, what will eventually happen? It forms a very hard outer covering that we call bark. So the epidermis changes. It doesn't become that nice soft, all right? What happens? The epidermal tissue, all right, they differentiate, they change, they become something else. They need to be, because otherwise, literally, the plant will burst at the seams, okay? So what happens to the outside part, all right? It changes to cork cambium, and that hardens, and that is what we call the bark, all right? This inner part over here is what we generally use the term wood, right? When they make furniture, etc., they're going to be using the xylem part of the wood. Now, you will notice over here, all right, if I go back, I'm hopping, I hope you don't get too seasick over here. I said that the plant, the stem, was able to breathe, all right, through these stomata. Now let's go back. If we think about bark, the bark of the tree is far too hard. It cannot, all right? So what the plant develops, the stem, all right, it develops, they look like that, they're cells that divide, and they've got a little hole at the top, and they are called lenticels. All right? So on a dicotyledonous stem, all right, the plant is able to bring in oxygen, carbon dioxide, gaseous exchange, all right, through lenticels. Okay, through lenticels. So here we have the outside changes. I put more xylem down, I put more phloem. Next year, more xylem, more phloem. More xylem, more phloem. More xylem, more phloem. Right, and what does my tree do? It grows wider. Right, secondary growth, secondary thickening. Okay, all right, let's do a few questions, all right, on secondary thickening and see if you can understand the concept. As I said, I showed you there. We had a nice little view of the actual thing, and I have now lost question number 1. It has disappeared. All right, we are going to question number 3. Okay, question number 2, right, is just a little, it's not even a comprehension, okay? Question number 2 is given me, it just gives you a picture. Let me just read through it. The geography, one of the geography teachers says it looks more like a geography question. But remember what I said to you? Sorry, I'm turning and going. Climate, the different climate changes, or the climate, or the weather conditions for that particular year, the climate for that year, right, is going to have an influence on the growth of the stem. So if we have a mild, moderate climate, all right, where we have definite seasons, where we have a colder winter and a warmer summer, we're going to have far more definite annual rings. Okay, so let's see over here. We're talking about El Nino and its partner, the warm and cold phases in the eastern half. Okay, events, okay, predicting El Nino events is now routine, but predicting how they will change in a warming world has been hampered by the lack of records available. Tree ring records from North America, particularly from the US Southwest, can be used to identify the intensity of El Nino and El Nina. Okay? Telling us about the climatic conditions over the past 1,100 years, and can be used to improve their prediction in climate models. During El Nino, the unusually warm surface temperatures in the eastern Pacific causes unusually wet winters in the US, while the colder eastern, during El Nino lends to drought. All right, have a look at the weather conditions. All right, when would it be best? When will the tree grow best? Okay, so first of all, just from that, our one question, what forms tree rings? All right, what is it? What is it that forms? It's not secondary thickening, that is the process. What are we seeing? We're seeing, all right, yes, new xylem tissue, right? That is what causes the xylem, the new xylem laying down, right? Because the phloem is not as noticeable. The xylem is the one that is going to cause, they grow, they show more, they're more of the annual ring. So it's a laying down of the xylem. Okay, so here, the next question. Explain how scientists would know whether a certain period was wetter or drier by looking at the tree rings. Right, this leads to the challenge question. Right, this leads to the challenge question. As I said to you, different climatic conditions will have an effect on the size, right, of the annual ring. So here, explain how scientists would know whether a certain period was wetter or drier. Okay, so let's start. They want to know when it's wetter, the annual rings are, let's have a look if we had to draw a tree. Okay, let's start. If it was wetter, lots of water, all right, water available. Now it becomes drier. If it's drier, we don't grow as much. All right, so what happens? All right, so here, the wetter, the annual rings are further apart. All right, why? Lots of water. All right, if we got water, we're going to have growth. Right? When it is drier, what will happen? The opposite. The annual rings will be closer together. All right? There's not a lot of water. If it's drier, we lack water. All right? And if we lack water, we're going to have a decrease in growth. All right? Okay. Very often, that's a kind of question. Explain why the rings are together. Explain why they are apart. Let's go on to the next question. Question number 3 for those of you, right, I did this last year when I did the grade 10 one. All right, and I want to do it again because it's using the tree, the rings of the trees, all right, to show biological skills. Okay, so it's not actually asking you to do anything other than use the tree as a data. It is, all right? Because remember, what does the tree tell us? The tree, the annual rings, gives us, all right, the time period. So let's look at what we have to do, and you need to read the question very carefully. The age of a tree can be determined by counting the annual rings. The following diagram shows a section through part of a tree trunk. The bark and annual rings are clearly visible. Here is the bark, all right? And there would be the beginning of the xylem. So we start 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, 10, there we go, 11, because remember, that's the bark, and each of those from here is an annual ring. So already we know that the tree is 11 years old, just by following the rings. Okay, so that gives us, okay, the point marked X is the center of the stem of the tree. The dark rings indicate autumn wood, which is the boundary that represents the end of the growth season. Remember we spoke about it? Let me just quickly erase one part so you can see. All right, that is the dark. Oopsie. Oh, pen, we go. There we go. That would be our autumn wood each time. All right, remember the dark ring that we saw when I showed you the wood? The dark ring, all right? Because it's so dark, it makes the ring more visible. It helps us to count easier. Okay, so now we've got that. Now we have to do the first thing. First thing it says, use your ruler to measure the radius of the tree after every year in millimeters. All right, let's look at terminology. Radius. If I am no maths person, all right, but what is the radius? All right, let's think. Radius of the circle. Right, the radius of the circle. Think about it first. Okay, after every year in millimeters. Remember to measure from point X to the outside of the dark rings for each successive year. All right, radius. So if this was, now let's go back here. If I were you, I would get a ruler. And there we go. I would draw a line all the way up for X. This centimeters over here confuses you, all right? It actually doesn't need to be there, but the part of the question, do not pay attention to it because then you are going to get confused, all right? So what it wants to know, all right, is what is the radius, look here, measure the radius of the tree after every year in millimeters, okay? So you're going to take X is over there. All right, our first year, we're going to start. What I would actually suggest you do, all right, is I would actually as well, just so everything is equal, I'd put another line in there. Okay, so what we're going to be doing, we're going to be measuring at the same time each time. Now remember, as I said, this is confusing. What do we want? Millimeters. Okay, I'm just going to make up ones. So our first one, year 1, you would measure from here, all right, from there, from X to here. That would be 1. So I would say 20 millimeters. Each time from X. Okay, put on X. Let's go to ring 2. There's ring 2. Sorry, we're not. There we go. A little bit. I'd say second year. All right, I would say 27 millimeters. Right, and so I would go for every single, it should be on the green, you know that, from X every single time. From X, okay? So I've measured each time from X to the line. From X to the line. From X to the line, okay? And then I've written all of that down, and now I've got data. Because question number 2, right, is testing my tabulation skills. All right, in a table, so we're going to draw a table, all right, and when we draw a table, all right, what do we need? Let's have a look over here. There's the outline for starters, and I'm going to need columns. Now it says draw a table in which you express your data in terms of the radius and the diameter. Okay, oh, cook. Sounds like maths here. All right, now let's start. Our very first column, what do we always put in our very first column? The independent variable. All right, and what you were given was the year. All right, so in your table, you're going to have year 1, year 2, year 3, all the way up to year 11. There we go, your year. All right, because remember, from one dark circle to the other, that is 1 year. It's a winter, a spring, a summer, and an autumn, which makes up a year. Okay, then all that information that you put in, they asked you for radius, so you put radius, and you put millimeters, because what can we not have in a table? Units of measurement. So 20, 27, 30, 34, all right, all the way. What is a diameter? Isn't it, if I circle, radius is half, all right, the diameter is the full length from point A to point B. So, times by 2. My diameter, it doesn't matter what I use with the information, my diameter is also in millimeters. 20 times 2 would be 40. All right, so all they've asked me to do is take that information and to plot it. I haven't got any information other than the fact that I've got the width of the tree rings. And from that diagram, I've got a whole lot of data that I can then express and I can put into a table form. All right? The last one, again, now using your table to express the growth rate of the tree trunk over time in the form of a graph. All right. How would I do that? I have got years. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now here, all right, it doesn't matter what you use. If you use the radius, millimeters, or the diameter, doesn't matter which set of information. All right, what are you going to notice? You plot it. Year 1, what was it? Year 2, what was it? Year 3, what was it? You join all the dots, and what should you notice? As the tree gets older, so the trunk gets wider. This one's klaar. Old phone girl.
Break time.
Break time.
Yes. Mine says you are going to take a break a reminder to enter this competition, Casio competition, guys. All you need to do is fill in all your information and answer all the questions from the Taste Yourself competition, and then the entry form is on our Facebook page, guys, so you have no excuse. And remember, entries do close on Friday. Congratulations once again to Qini Sombalana for winning this awesome calculator. With that said, let's take a very quick break. We'll see you straight after this. Hey, we're back. Hadi. Are you ready for questions?
Are we
Now,
going to do? Are we
do you
going
want?
to
Okay,
have to do the
okay,
challenge?
do
I have
the.
to
Okay,
because you know I always
can.
forget the challenge
Okay,
question.
do it first, and
Okay,
then.
we're going to do the challenge question because I usually forgot, and then Looney's got lots of questions that she's going to
Yes.
ask me. Right, if you had listened carefully, all right, throughout, you would have listened to where we would see more distinct annual rings. Okay, so let's have a look. Annual rings are distinct. Didn't say that they are. Yes, all of these regions probably could have, but where? Temperate, tropical, polar, Arctic. Okay, 3 and 4, very, very cold. All right, so the rings are probably so close together you can hardly see. That's not distinct. Tropical, all right, hardly has a winter, so it's going to be moderate throughout, so we're not going to see that distinct growth pattern. So temperate is our answer. That's our winner, yay, because what do we have? Are you laughing?
What is that?
It's an NB. Must I put an NB? Oh, no, that
Wow.
didn't even come out. There,
Okay.
NB. Okay, number 1. Do you want me to? There, number 1. All right, is the answer, because we're going to have different winter and summer, and because we have the seasons, it is much easier to see our annual rings.
On Facebook, it's A, B, C, O, D, so it's A
Yeah. Oh, is it A? Is it?
on Facebook.
Okay, so A, B, C, D, A for A, K.
There you
got it
go.
right. Okay,
All right.
hit it to me.
Okay, first one, Jacqueline Malachi. Can you
Okay.
please explain the functions of the Diecut stem?
All right. Okay, the functions of the dicot stem are the functions of the same as a monocot as well. All right. If we have a look at our stem, what's its function? Okay, number 1, it's going to hold the leaves in place, because if it holds the leaves in place, all right, we can have sunlight for photosynthesis. It also has, oh, let me draw a flower. It's also going to hold the flowers, all right, obviously for pollination to occur. And next week, all right, when you listen to the show, it's going to, remember we did the root, all right, the roots, water comes into the root and water must go up the stem, all right, so it's a transport organ as well. Okay, so it supports the leaves and the flowers, puts them in position, and it's going to transport water up the stem, and it's going to transport food down the stem. Sharp.
Okay.
Okay.
And then, Master K, how can we calculate the age of a tree or a plant?
Okay, right. Let's go back. Let's go back to Okay, let's use this diagram. Right, as I said to you, each ring shows, all right, now I'm going to show you here. Let's do this. This is bark, all right, and called cambium. That was the epidermis, and I think that's one of the questions that somebody asked as well. Okay, so listen up. I'm going to try and answer the 2 questions at once. Epidermal tissue and the parenchyma tissue change, all right? They change to become what we call cork cambium, all right? So it takes over the parenchyma totally, and it's obviously a much harder tissue, and on the outside it forms the bark, all right? So it changes. Remember, meristematic tissue can change. Now, what we have is here, when we looked at the, right, at the vascular bundles, we noticed, there we go, that we started, the xylem, all right, was in the inside. Here's my xylem, that's on the inside. Every single year, I lay down more xylem. There we go. Do you notice? there's a ring. Okay, so let me use a different color. So that pink is one ring, which means it's made up, the darkness is growth during winter and autumn. The lightness is the growth during summer and spring. This, so from here to here is 1 year. Okay, so that's my second ring, 1, 2. That's my third ring, 3, 4, 5, 6, 7, 8, 9, 10, 11 years old as well. Each ring, the gap in between, is a year.
Okay, cool.
Shanana.
What?
Shanana means sharp.
Okay. Mabilam
Yeah,
Kondo
you
is
were born way
asking.
before
No,
I
it's
was.
fine. It's
Well, I was
fine.
born way before you, so yeah.
How can you identify as to whether a plant is male or female?
Okay. Now, that all depends on the flower, all right? And we haven't done the flowers this year, but I am going to tell you, all right? You need to understand that some plants, all right, are both. All right, let me just extend it. I can just extend. Hey, there we go. There we go. All right, extend. Okay. When we look at a flower, you're going to be doing this next year. Okay, a flower, that's the only way you're going to notice. In the center, have a look. You're going to see a female part, and most of you recognize the pollen. That is the male part. Now, usually, believe it or not, the flowers are both male and female. All right? If it's a male plant, it will just have these, what we call stamens. And if it's a female plant, all right, it will just have the female parts, what is called the pistil. But we're going to be doing that next year in grade 11.
Okay, cool.
Yeah.
Moya habo mahato. How is Xylem modified for its function?
Okay, Xylem, very important. All right, very important. Xylem, all right, so let's go. Oh, let's go. Extend page, extend. Okay, my page is not extending. Okay, let me go down. I will get there. I will get there. Oh, there we go. One more time. Okay, Xylem. All right, what is its function? TPT means transport. It needs to transport water. Okay, so let's have a look. To transport water, 1, it's hollow. Remember, think of a straw. If it's hollow, water can move up easier. Okay, easier movement. Imagine if you get a piece of paper or something stuck in your straw, not going to work. Number 2, it's thin. All right, you're going to do that next week. All right, I'm sure all of you have done this. I want you to take a straw. You stick it into your Coke can. I'm sure you've all done it. You've put your finger over the top and you've lifted it out of the Coke can. You've done it.
Yes.
You see. Okay. That's how a plant works. All right. You've actually done a scientific experiment called capillarity.
I didn't even know.
You didn't even know it. Life science in everyday life. All right. That's what happens. Nice and thin. Do you notice? So what moves up your straw? All right. Your Coke, in this case, water. The thinner it is, the higher, all right, the water will move up. Second of all, well, actually third, let's go 3. It must be lignified. Because the stronger it is, all right, water force, the force of water is very strong, all right? So it's there to support, all right, and take the force of the water. Another one, all right, number 4, it's continuous. If you have got a big plant, you put one on top of each other. It's a bit stupid if your water only goes halfway. So it's continuous. All right, also, what does it have? Number 5, it's got little pits. When you get into an elevator, you don't have the choice of bottom floor, top floor, all right? What happens in between? If you're a plant, all right, what about all these branches over there? Isn't the whole plant needs water? Right, so you have these little pits, okay, and the water moves out of them. You're going to learn next week. It's called translocation. Voila. Shanana.
Hey, these things of yours. And then Spencer Clemandla is asking, what is the difference between cambium and lateral meristems?
Okay, lateral meristems, all right, cambium is lateral meristem. In the root, we call it pericycle, and in the stem, we call it vascular cambium. All right, it's a difference between a toe and a finger.
Okay.
All right, it's pretty much the same thing, but yeah,
Can
slightly
we
different.
take one more? How did oh no, it's going away now.
Oh, is it
How does
going
the
away?
temperature and plant combine?
How does the temperature in the plant?
Yes.
Remember, all right, not how does it combine. If we have a look, let's go again, all right. For a plant, the milder the temperature, when we talk about mild, we've got sunshine, which is light, we've got water, right, and if it's got everything that it needs, it's going to grow better. It's the same as you. If you've got more food, you're going to grow better. If you don't have enough food, you're not going to grow at all, very little. And that's exactly with the plant. The more sunlight, the more water, the bigger it's going to grow. The colder, the less water, the less it's going to grow. Sharp, sharp.
Thanks.
There we go.
Thank you, Cheryl, for the awesome lesson. Mindsetters at home, thank you so much for tuning in and for interacting with me on Facebook and on Twitter. Remember to catch us next week, same time, same place. Goodbye.